and of course they gave in pound per feet square, is equal to 0.4. Its relation is very simple, 0.4 into diameter, and that diameter is in inch. Diameter is in inch. And now, say nowadays in India we are using, say, diameter in millimeter or say centimeter we will be talking about, and then we are not talking about pound per feet square, we may be talking about Newton per meter square, kilonewton per meter square. So that way, if we use this equation, then this relation, then we need to convert the unit, and this is well known how we can convert from inch to centimeter. Just to give readily how we can have pound per feet square to kg per meter square, that we can convert as 4.882 kg per meter square, 1 pound feet square is equal to that you can have. And if we want to convert it to Newton, then we multiply it by 10, like that, kilonewton, 1000, so like that we can change these things. Well, so that way we can have the value of, say, tractive force at bed of the particle, at the bed of the channel, by using the relationship given by USBR. Okay, this is directly giving us permissible tractive stress. Well, but again, as we have just discussed, that we were discussing Seal's theory also, and then from Seal's theory we got a curve, and from that curve ultimately we could derive the tractive stress, or this we gave as critical tractive stress, tau c we were writing by Seal's equation, and there with tau c, if we keep in kilonewton per meter square and say diameter of the particle in meter, diameter of the particle in meter, say d diameter in meter, and tau c is in kilonewton per meter square, then we could see that Seal's equation gave us a relation like 0.06, then unit weight of water, the g is the specific gravity of the soil, and then -1 into diameter of the particle. That simplified equation we could get. And that equation, if we simplify further by taking the standard value of W and by taking the standard value of say soil, maybe 2.65, like that, the soil is specific gravity, then we can get a value tau c is equal to nearly 0.98 into d. Okay. Well, then White equation is another equation that gives us critical tractive force or critical tractive stress tau c as 0.801 into diameter. The unit is same. And then Lenz's equation is another equation which is generally applied when the flow is when it is a fully developed turbulent flow. In that case, our tractive force is at little lesser tractive force, the particle starts moving for a fully developed turbulent flow, and then tau c is given as 0.78 into d. So these values can also be used for determining the permissible tractive force or permissible unit tractive force, or the permissible tractive stress at the bed. And what is that? That is, permissible tractive force can also be taken as 0.9 of tau c. Here we are getting tau c, and then by this method, if we calculate the value and then we take the 0.9, that is 90% of that value, then that we can take as permissible tractive stress. And then if you just try this calculation, then from this calculation, if we do, if we just try this calculation putting for standard values, then we find that we get almost an expression of 0.76 d. This will also ultimately lead us to a value. If we change this unit, it will lead us to a value of the 0.76 d around. And then here it is tau c, and then we need to take 0.9 time of that. So more or less we are at almost near a value that we are getting. And so we can see that to be on safer side for our design purpose, we can take it tau c as say 0.76, tau b permissible tractive stress as 0.76 d or 0.75 d, around that we can take. Of course, if we have confidence, if we know the soil in a much better way, and flow condition we are sure about, that it will not be that turbulent, and then we can take our tractive force little higher value than our, if we take the tractive force little higher value, that is permissible tractive force little higher, our size of the channel will be lesser. So I mean, if we do not want to be that much conservative, then we can take little higher value, or otherwise we can go for lesser value. Well, that depends on experience and knowledge of the soil formation. Well, then what is design principle? What is design principle? So design principle, let me just explain it step by step. You can refer to the slide. The design principle is that unit tractive force exerted should be less than the permissible unit tractive force. That we have already explained, we are repeating, but as a design principle, the main steps, we must say that this is the first principle. Well, then starting with this principle, then we could see that tractive force ratio, we calculated one, that we name as K, tractive force ratio K is equal to say tau S by tau B. And this ratio indicates that tractive force required to move vertical at side is less than that required for the bottom. Well, and therefore, for design purpose, what is done, that the channel is designed based on the side tractive force. This is the standard procedure we follow for design, is done based on the side tractive force, because in the side the force required is less. And of course, there is another point that we are getting, that at the side the force required is less. So this is more critical. If the side is safe, generally bottom will be safe. But another point, we need to note that if we just go back to our this curve that we did discuss, we are discussing this curve, then if our B by Y ratio is high, then the force exerted the bed is higher. And for otherwise also, normally these are steeper. In bed, the tractive force exerted is also higher than the tractive force exerted in the side. So we know that tractive force, resisting tractive force of the side is less, but at the same time, force applied is also less. But of course, for high value of B by Y this is significant, but for low value it is not that much significant. So generally, we design it first for, say, tractive force at the base, and then tractive force at the side tractive force, we design it first, we see what the value is coming, and then we are getting a size, and then its safety against bottom tractive force is checked. This is the conventional practice we follow. However, when we have a computer, then these calculations will not take much time, and in fact, if we have the curve, and then we can just represent the curve also by some equation, and then this can be done very quickly. And then what we can see, of course, one can calculate the depth from the consideration of both side and bed tractive force. That means depth we can calculate from both side consideration, we can get one depth, from bed consideration we can get one depth by using both the tractive force value. One is permissible, another is what is exerted. So from both these values we can get one depth, and then of course two depth we will be getting. Out of that, what is the smaller one, that we can consider for our design purpose. But conventionally we find that for the side, what depth we will be getting, that is the smaller, because the side is more critical. Still we can go by this way also, what I mentioned the last. Well, then we need to follow some design step for tractive force method. First, what we do, that we consider a B by Y ratio. Well, we need to assume a B by Y ratio based on the availability of space, and with some of our understanding that depth will be this much. Okay, suppose we know that this is the discharge, and for that discharge, this much will be the depth around we want to flow in the channel, then, well, that should be the B. So we can try with B by Y ratio from our experience. And then we are assuming a B by Y ratio. And the side slope is assumed. So this first B by Y ratio we're getting, then side slope is assumed based on the material property and the value of theta is obtained. Well, a side slope, as we did discuss, that for this particular material, this will be like that, although it is alluvial, but still based on our understanding, still there will be some variation. Alluvial means the particle size may be still larger and smaller. Well, that way we decide what should be the side slope. And then once we decide the side slope, well, we'll be getting what is the angle theta. Well, then once we get this theta, that is Z value is known. Z value is known. This will give us the Z value. Then maximum unit tractive force tau s at the site can be obtained in terms of WYS from the USB curve. We have just shown that particular curve from the side tractive force and bed tractive force. We have sets of curve for different Z value. We can find those tractive force that is at side and bed. Of course, that will be in terms of WYS. That is some fraction multiplied by WYS. And then another important value we need to know is that angle of internal friction phi. So that angle of internal friction we need to calculate. Rather, calculate means we can have our analysis in the laboratory, or there are some standard curve which provide the value of angle of internal friction. In fact, USBR gave some curves which give us the value of angle of internal friction based on the diameter of the particle. Well, those curves can be used. We can do experimentation in the lab. We can find the value of phi. So that way somehow we need to find the value of phi. Then we need to calculate the tractive force ratio K, which we know that there is an expression. We can find that. Well, the next step will be permissible tractive force tau B is computed. So tau C, we can use the expression of USBR, or we can use tau C for that Seals equation or White equation, Lane equation. Then we can, from any of these, we need to calculate finally the permissible tractive force at the bottom. So once we get the permissible tractive force at the bottom, we can get the permissible tractive force at the side by the equation that it is tau S is nothing but is equal to K into tau B. Well, then equating permissible tractive stress at the side and the tractive stress exerted, which we have obtained from the assumed B by Y ratio and value of depth B by Y ratio, so that we can equate, and from that we can get the value of Y, depth Y, and B. Y, first we will be getting the value of Y, and then we know the B by Y ratio, so we can have the value of this B directly from that. And that we are getting tau S. How we are getting this tau S? That we can get tau S is equal to that fraction multiplied by WYS, and after that we are getting the depth and B value. So this is what is our required design, but of course this is not the final design. Then safety of this design we need to check against the tractive force at the bed. Okay, so then once we check the tractive force at the bed, suppose we have found it to be safe, then we need to check whether this size is enough to carry the required discharge. So carrying capacity of the channel is checked by computing the discharge by Manning's equation. Now our size of the channel with us, then slope is there, so we can calculate how much discharge it can carry. If this is the depth Y, then if it is just sufficient from our required discharge, then this is our final acceptable design. And if it is less than our required discharge, then we need to repeat the entire procedure by increasing the B by Y ratio. So we need to increase the B by Y ratio, and then we need to carry out the entire process to get a new dimension for our channel. So that way we get the channel dimension, we check, and if it is sufficient, when it is just sufficient, then we solve. Suppose in the first trial we have found that okay, it is sufficient, but it is much more than the sufficient, then we can reduce the B by Y ratio. Rather, we should try with smaller B by Y ratio so that we can just get from insufficient, then we are moving into just sufficient. So that is what we can do, and once a computer program is developed, then we can do it very easily. Well, then after designing the channel, we need to add a freeboard to the channel. What is meant by freeboard? Say our design depth is this one. Then we need to keep some extra over this for our safety, that is called freeboard. That is called freeboard. So that extra depth we need to provide. And Indian standard and USB has also suggested, say Indian standard means basically Central Board of Irrigation and Power has suggested some value that if the charge is less than 0.75 meter cube per second, the freeboard required is 0.45. Why I am giving this value? Because freeboard is not that negligible. Suppose sometimes we may get our depth of Y water is 0.5, but above that we need to add say 0.45, almost 100% freeboard. Okay. I mean, then suppose for a depth of 0.75 to 1.5, not depth, for a depth of 0.75 to 1.5 meter cube per second discharge of this value, we can have freeboard of 0.6. And then for there is a large range now from 1.5 to 85 meter cube per second. That range is very large, and for that we need to add 0.75, and then if it is greater than 85, then we need to add almost 1 meter, is 0.9 meter. So what we should get, that it is not uniformly with the increase of discharge, it is not proportionately increasing, but it is increasing definitely. But for a very large range of discharge, we may keep the freeboard as 0.75 meter. So that is how we add the freeboard, and finally we get our required design for the channel. Well, here we are concluding our discussion on alluvial channels, and we are not taking up any numerical. Of course, we didn't take any numericals, and I hope that we have tried to explain the steps very well so that there will not be much problem in doing some of the numerical example. But this practice is essential, and I hope that we will be able to have better understanding of all this method, Kennedy's, Lacey's, or tractive force, by taking some hands-on and by doing some practical example. Thank you very much.